This is where the class starts getting hard and and fast. We got lots to cover. So you need to carve out more time outside of class. I know it's a busy time of semester, but if you want to succeed on this final, you're going to have to up the time spent outside of class on this. And in general, like not many of you, like none of you come to office hours actually for help on this stuff, and it's kind of surprising to me because it's hard. Like we can't get through it all and do a really good job in class. We just don't have the time, and so I would expect that you would be coming to office hours to get help. For whatever reason, you guys aren't. So now's the time to start. So office hours Monday and Wednesday afternoons. If you're getting stuck on these problems, come in and let's talk about them. Okay, let's work on them. All right, so before we start this, I just want to give a general, let's do this first. Okay, so what is our RUV? What is this? Parameterization of a surface, right? It takes two variables to parameterize a surface. Okay, what about F? This is the vector field that we're in, right? What is S? What's the S vector? It's an area vector. Its magnitude is area of the surface. Direction is normal to the surface, and that can change, right? If it's a curved surface, the normal will change. All right, so then just S, just the area of that, right? Without the orthogonal direction. So then what's ds? What's the ds vector? What's the ds? If it's the same as this, but a small version. But we didn't say this was a change, right? This wasn't a change. What was this?
The whole thing.
What is it? You just said it. It's the area vector, right? It's the area vector. So ds vector is? It's not change. It's not change. Don't think of it as a change. It's a two-dimensional element. So kind of, but it's a small area vector, right? It's like an element. It's an area element vector. Area vector element. Anyway. So it's like the area vector for a small element. That's what I'm trying to say. It's the area vector for a small element of your surface. Right? So if you have some surface, we partitioned it. We partition it in terms of U and V. And so that gives elements, right? So that when you partition it, you're kind of slicing it up. That makes elements. Each one of those little elements, ds is the area vector for the element. And so what is its magnitude? Area of the element. What's its direction? Normal to the element, right? Orthogonal to the element, which then is orthogonal to the surface. All right, what about just ds? Area of the elements, right? Just the area without not being a vector anymore, okay? Oh, so let's go back and say, what do these equal? What does ds equal? What is the ds vector? Remember?
RU cross RV
Mm-hmm.
times 2UV.
Right. Right? So the RU cross RV gives us a vector, cross product gives orthogonal. So just think like parallelogram, like that. This is just the vector for when you take the cross product of the two parcels, which are parallel to the ends of the element, you get the area of the parallelogram as the magnitude, and the direction is orthogonal, and that's what that ends up being. Right? So this is a vector whose area is the area of the element, because this is basically has the area of the parallelogram, and whose direction is orthogonal to the element. So then what's just ds? Magnitude of the cross product, right? du dv. Let's just say magnitude ru. So when we're doing surface area, we're not doing a flux in a vector field, right? So forget about the vector field. You just have the surface, and if you want to calculate the surface area, then you're going to integrate all these area elements, right? So integrate over S, and this will give surface area. So there's like two kinds of this surface integrals. Just finding the area of the surface has nothing to do with being in a vector field. It's just finding the area of the surface. Then we talk about flux. That brings the flux is the flow rate of the vector field through the surface. So that's going to bring F into it. What is N? That's the vector. It's a unit vector orthogonal to the surface. All right, and then what is our flux? So our flux is then the flow rate of F through S. And so we have to do that an element at a time, right? We're going to do that one element at a time. We're going to take We're going to take the F at every element parallel to the S vector or orthogonal to the S vector? Parallel to the S vector, because the X vector is already orthogonal to the surface, right? The S vector is orthogonal to the surface. Then we want the part of F that's parallel to S, because that's the part of F that's orthogonal to the surface. So that means what? Dot product of F and ds. Now, there's another form for ds that in certain situations makes your life a lot easier, and that is n ds, right? Because if ds is the area and that's orthogonal to the surface, the unit vector orthogonal to the surface, that's exactly what ds is also. So these are two versions of ds. There's this and that. And so we can write this as two different ways. We can write it as f dot nds or f dot ru cross rb du dv. That's an F, not a P. Okay, this will always work. Okay, this will always work. I only recommend using this. We're going to use this in this situation. When you have a planar surface parallel to a coordinate plane. So it's a really, really specific situation. I think that this is convenient. But if you don't have that situation, I say go with this. All right. So when do you use that? So S is parallel to S is a plane parallel to a coordinate plane. Oh no. That's when I would suggest that you use that. Any other situation, if it's a slanted plane or any other curved surface, we're going to go with this. We're going to use this version. All right, so now, that being said, this capital S kind of has a dual, it can be used, depending on the context, used in different ways. It can be the area of an area vector, but it's also just a generic name for a surface, like they just call the surface S. So you got to be careful, like how is yes being used in the context? So from here on out, most of the time S is just going to stand for a surface. You'll have like S1, S2, S3. Okay? Like E stands for a solid, C stands for a curve, and D stands for a region. Those are the most common letters that we use to take on these geometric quantities. Okay? So we said S was the magnitude of the area vector. You'll also see commonly S is just a symbol to represent a surface. Does that make sense? I just want to keep heads up for that. All right, any questions on all this? Gotta have this straight. So let's do examples. Questions? Okay, here's one. We want to find the flux through S. So S stands for this surface. The part of z equals 4 minus x squared minus y squared that lies above the unit square in the xy plane. If F is xy, yz, xz. So that's a paraboloid opening downward with vertex at 0, 0, 4. We've got a curved surface, so we're going to use this form, the F dot RU cross RV. I'm not sure why I reversed it, but it's the same thing. Dot product order doesn't matter. So what do we need to do? Parameterize the surface, right? So we need to get what? So what are we going to choose for U and V? What two variables are we going to choose? So this is what you did over the weekend, parameterizing surfaces. C equals 4 minus x squared minus y squared. Paraboloid opening downward. What are you going to use for your two variables to write every point on the surface? Okay, someone suggested x and y. Can we write it as x and y? Okay, and what would it be? X, y. Right, that's the easiest. Okay. Would there be any other possible way we would do this?
Use R and theta.
R and theta, right? So we could use R and theta because this is a paraboloid centered on the z-axis. So maybe R and theta. But there's a better, there's one choice is better than the other here. So think about this. In the end, if we do x and y, we're going to be doing a double integral with respect to x and y. If we do r and theta, we're going to be doing a double integral with respect to r and theta in the end. So thinking about the double integral that we'll have to calculate, one choice is clearly better than the other. Polar is better? Yeah, look at what we're integrating over, right? We're integrating a square. We're not integrating over something circular. It's a square. So x and y is going to be far better because x is going to go from 0 to 1, y is going to go from 0 to 1. You don't want to do this in polar, right? So even though the surface is very, fitting for polar because it's this paraboloid, we're integrating over a square with super easy limits for x and y. So we're going to go with x and y. Okay, so we need to find partials Rx and Ry, right? And we're going to do the cross product of Rx cross Ry. And that's, remember, we're going to use our determinant algorithm with ijk, Rx, Ry. So what is the partial with respect to x? 1, 0, negative 2x. Partial with respect to y? And then we're going to run the cross product algorithm here. And when we do that, we get 0, positive 2x. J is positive 2y, and 1. So Rx cross Ry is 2x, 2y, 1. And we're ready to go. So we're going to integrate f. Now f has to be written in the two variables that are surfaces, right? So we're going to have to rewrite this in terms of x and y only. So x component is xy, y component yz. Right? Zx. Dot. And our u and v is x and y. So dx, dy, and then x goes from 0 to 1. So these flux integrals, these surface integrals, and these flux integrals, they just boil down to double integrals, right? So then everything you learned about double integrals applies, right? Type 1, type 2, polar, etc. And that's going to be what? The flow rate of f through that surface. And is the orientation up or down? So that flux is going to be relative to upward flow being positive or downward flow being positive? Well, if you think of, we've got a little element of that surface. There's a little ds element. And so we calculated Rx cross Ry. And what do you notice about Rx cross Ry? Will it be pointed like, so will it be pointed like this or this? Y up. The z component of our Rx cross Ry is positive. So our little area vector, our ds vector, is pointing up. So this flux is going to be relative to up being positive. So if you get a positive number, then most of the flow is up. If you get a negative number, most of the flow is down. Because our little point, this positive one in z tells us that our point area vector, or our area vector points in the positive direction. That's how this was the orientation of the surface, right? This is the orientation of the surface, upward orientation. And had we done Ry cross Rx, then we would have had downward orientation. We would have gotten a negative 1. Questions on this example? So then there's a lot of algebra to do, but there's nothing hard left.
On the exam, could you expected to finish that integral, or could we just leave it at that? Since that's
It depends. I mean, this is just algebra, right? So depends what it asks for. But my interest on that exam is not that you do long algebra problems. Okay, so probably I might ask you something like this just to set it up. If there's something simpler with the algebra, I might ask you to solve it. But my interest in the exam is not that you're spending 10 minutes on algebra on a problem. Other questions? All right, next example. Oh, so before we do the next example, what we can do here is we can derive a general form for the flux when the surface is parameterized in x and y. So when a surface is parameterized in x and y, let's do some of the math in that generic case and see if we can get a version of this that's a little more streamlined. Because we expect we're going to have lots of surfaces that we're going to use x and y as the parameterization. So rather than, like in that last example, going through the cross product every time, let's just do it once and see if we can get a formula that's a little more streamlined that's equal to this. So what happened? We did yep. So the partial derivatives are what's the partial derivative always going to be? Rx and Ry. Rx is going to be 1, 0, the partial of g with respect to x. And then this will be 0, 1, partial g with respect to y. So Rx cross Ry is going to be the opposite of gx. It's the partial of g with respect to x. Opposite gy and 1. So if you're parameterized in x and y, your Rx cross Ry will always be this. And then we can write, and our f we can write generically as p, q, and r. We've done that, p, q, r, right? So then we've got p, q, r dot gx, gy, and 1. And that's what this is right here. So what is that? Negative p times the partial of g with respect to x. That's negative. Minus q times the partial of g with respect to y. Plus r. dA. So either dx dy or dy dx. Okay, and so whatever our region is, say D. A region D in the xy plane. So you can do type 1 or type 2. Probably you're not, if you parameterize xy at the start, you're probably not going to do polar. So then it's either type 1 or type 2. So here's a much more streamlined version. You don't have to do the cross product. Just go right to this. If your surface is using the variables x and y, and then g is your z as a function of x and y, then you can get your flux. You can just use that right away. So we could have used that on the last problem. Instead of doing the cross product and writing the dot product, like we ended up with, we could have gone right to this. So in the last problem, that would have been what? What was P? Anyway, let's not take the time to do that. But in the last problem, this would have been perfectly applicable because we were parameterizing that surface as x and y. Any questions? So let's get to a longer example. So the previous example we did, was that flux through open surface or closed surface? The part of the paraboloid over the square. That was an open surface, right? It had like a top side and a bottom side. So let's do one for a closed surface. Find the flux through S, the closed surface, that is part of the unit cube below y plus z equals 1. If this is our vector field, xy, y squared z, with inward orientation. So can you sketch that first of all? And the unit cube is entirely in the first octant, right? So it's a cube of side length 1 that lies in the first octant with a corner at 0, 0, 0. But we want the part of the cube that's below y plus z equals 1. Can you sketch that? So what's the part of that that's below y plus z equals 1? Okay? So y plus c equals 1, how does it cut this thing?
It'll cut like, it'll like make like a triangle, at like from 0, 0, 1 to 0, 1, 0, and a line going to there, and then extend it out to x equals 1.
Well said, right? So you can start with the line y plus e equals 1, and this is like a linear cylinder, so it's a plane, extending out in the x direction. So we're going to chop off whatever's above that and take the part below that red plane. So in the end, we get half of the cube. That's right. So did you have that before I did it? Hopefully. All right, so then, so what does it mean to do the if we're talking about the closed, the flux through the closed surface, what will that mean for the solving process? The inward orientation flux through that closed surface.
Does that mean you have to have 3?
More than that.
Oh, every side, I guess. So
Yeah. How many sides are there?
it's like 5.
5 sides, right? So we're going to have 5 different flux integrals, and then we're going to take the cumulative effect of all those flux integrals, add it together. So let's call the bottom, it's going to be S1. And the left side is going to be S2. And the front, S3. And the back, S4. And then the top will be S5. So notice that S1, S2, S3, and S4 are all planes parallel to coordinate planes, so we can use that one form that I said. We can use, so for S1 through S4, use F dot and ds, because that's a lot easier. It's going to make life a lot easier than finding dot products, okay, or finding cross products. All right, so we'll start with that. S1. So for inward orientation, we need n. What is n? So F is, so for S1, we know z equals 0, right? Therefore, F is, we can simplify F because z is 0. So F becomes X.
So like 0, 0, z.
Why do I have X comma? Oh, that's the parameterization. That's F. So yeah, so F becomes xy, y squared, and 0. Okay? And then all we need, instead of parameterizing the surface, all we need is n, right? So here, notice there's no rx, ry, ru, rv. It's just f dot n. So we need, what do we need n? We need the unit vector orthogonal to the surface with inward orientation. What will that be? 0, 0, 1. So we don't have to, the benefit to this is we don't have to parameterize, we don't have to do cross product. We can just write the n and do a dot product and pretty much be done. So we're going to go integrate f z is 0 on the surface, dot. And that's going to equal what? 0. The dot product is 0. It's double integral 0. That was easy. But the setup, doing all that setup work is valuable, right? So yes, everything canceled out, but understanding why f is what it is, why n is what it is for S1, that's valuable. So why don't you guys try to do S2, S3, and S4. See if you can use the same technique, f dot n ds, to get the integrals for S2, S3, and S4.
But I'm still looking at something. Forms of kids. Well, not
So we actually get to something interesting with surface 3, the front surface. Do you agree with what I did?
Yes.
Winston does, Chrissy does. Yep. Any questions on S3? What's that? Why is it negative 1, 0, 0? Inward orientation. So inward orientation from that plane will be in the negative x direction, right? That's why it's negative 1, 0, 0. And we're at x equals 1, so you can plug x equals 1 into your field. And then, did I do the math right? Is it negative 1/6?
Yeah.
Yeah.
Okay, good. People are getting that. So before I need to erase all this to have room for S4 through S6. So let's make sure we're good on S1 through S3. Any questions? Can I erase? Last chance. Last chance for S3. Okay, S4. S4, what's that plane? X equals 0. N is positive 1, 0, 0 for inward orientation, that's right. And then we'll have 0 y squared z dot with conclusion S5. Here's the last one. So what is S5? S5 is this plane. So we could make it work with the f dot n ds, but it's just as much work as doing it the other way. And actually, so like I said, only recommend using this for planes parallel to coordinate planes. So let's not finagle it to get it to work on this slanted plane. So we need to parameterize this one. What should we use to parameterize? It's an easy plane. Let's use x and y. So it's going to be z equals 1 minus y. But before we start, and then f is going to be? Xy, y squared, and then we have no z, so 1 minus y. Okay, before we start doing cross products and all that stuff, what do you notice? So in the last screen, before we did the start of the example, we derived a streamlined formula for this case when our parameterization is in x and y. So let's use that. What was it? Negative p. This is our p, q, and r is from our vector field, right? So negative p times the partial of g. Here's our g with respect to x. 0, right? Minus q times the partial of g with respect to y, which is negative 1 plus r. Okay, and then we're going to integrate over what? So it's that plane integrated over. So x goes from This is nice. 0 to 1, 0 to 1. Okay, but we have to consider something here. Right. Is this going to be outward or inward orientation? So remember what happened when we did Rx cross Ry? What was our Z component? For Rx cross Ry? 1, right? Which means this right now, the way we have it is Z positive, and that would be inward or outward? That'd be outward. So we got to take the opposite of this whole thing to get inward orientation, which is downward. Right? So that general case formula would be for Z positive orientation. If we need Z to be, or in the negative K direction, to be inward. So we're going to take the opposite of the whole thing. So what do we get for this integrand? Y squared minus y plus 1? Dx dy. So I think x just gives this back to us again. Is that right? Oh, negative the whole thing? So negative the whole thing. Y, single integral now. 0 to 1. So I think we're going to get the opposite of, it's going to be 1/3 minus 1/2 plus 1. Which equals negative 5/6. So the flux is the sum of all the fluxes of all the sides. So I think that's going to be 0 plus 0 minus 1/6 plus 0 minus 5/6 equals negative 1.